we have two propositions. D of x is taking discrete mathematics, and wx, x is wise. So if everyone taking discrete mathematics is wise, and Artavan is just taking discrete mathematics, so how do we represent everyone taking discrete mathematics is wise? We do that with a quantified statement, right? For all x, so all students, if they're taking discrete mathematics, then they are wise. I'll hold that to be true. Okay, that's my premise. Everyone taking discrete mathematics is wise. So now we found a new piece of information, and that is Artavan is taking discrete mathematics. So we want to prove that he's wise. And the way that we do that is we combine these facts, but we need the information that we just had. Okay? So we know then if we're using an assumed universe, and Artavan is in that universe of Dalhousie students, for instance, then I want to show that this holds. And I can do that from universal instantiation. What that means is if I have for all x something is true, then, and I have something from that set. So if this is true for all students, if you're taking a discrete math course, then you are wise. That's true for all students. And I have Artavan is a student, then I know that it must be true for him. And so then we know that this holds. That doesn't prove that he's wise. What it proves is that it would be, this implication holds. But then we have one more piece. We also know that one of our premises is that Artavan is taking our course. So D of S is our premise. So what does that look like? And you're going to have to think for a second, because now we're outside, there's nothing quantifying. But if I have D of S implies, W of S, I think my pen is dying on me. And I have this, what can I conclude from that? And this is from our last class. This, different letters, same concept. I have something implies something else, and that antecedent is then true. Yeah, W of S. Is it Artavan saying he's wise? No. And that is Modus Ponens. So this form, do you remember we had P implies Q? P, therefore Q. This is that we call that Modus Ponens. Does anybody remember what Modus Ponens means in Latin? The mode that affirms. Okay, so this concept that you affirm the premise, and then it shows that that implication, the consequence of that implication holds. This is Modus Ponens, the mode that affirms. And we're combining that this time with universal instantiation. It looks similar. So if we remember, this is at the top, this is Modus Ponens. Then it looks very similar, doesn't it? The only difference is that we've got this universal instantiation at the top. The concept is there. So you have for all x, you have some implication, P implies Q, and then you have that for some A in the universe, you can find that it's true. You can conclude that Q of A is also true. So then, remember, I gave you two named rules of inference. I gave you the names for the others, but the two that I said that I cared about were Modus Ponens and Modus Tollens. Does anybody remember Modus Tollens, the mode that denies? This one says P implies Q and Q is false. But remember, that this is the same as saying either Q is true or P is false. Because if P is true, then Q must be true, right? But but otherwise the only option is that P is false. Okay, so in fact, because that's the case, so essentially Q or not P, and we see that we have that Q is false, that tells us that we must have not P. So that was Modus Ponens, which is a recap. But if we add that universal quantifier into this mix, and then we apply this Modus Tollens, what we get is we say, if for all elements in our domain, in our universe, we have that implication, P implies Q, P of X implies Q of X, and then we find some element in the universe such that Q of X is false, then we know that P of A must also be false. What can we conclude from this? So here's examples based on what we just talked about. What can we conclude from this? So somebody in this class enjoys sailing. Every person who likes sailing loves the ocean. Somebody in this class loves the ocean. And essentially what we have is what? If you had to go backwards and say the form of Modus Ponens and the form of universal Modus Tollens, why can we say this? I mean, essentially, where does this come from? So essentially what we're saying, let's call it something real, and we'll call this loves the ocean is heart of X. What this line here says, it says every person who loves the ocean, who likes sailing, loves the ocean. And that's like saying for all X, if they sail, they love the ocean. And somebody in this class enjoys sailing is like saying there is a person, P or A, I cannot draw, that likes to sail. And from that, which is that? Universal Modus Ponens, the mode that affirms, or universal Modus Tollens, the mode that denies. Ponens, yeah, exactly. Because I've affirmed, I have affirmed that antecedent. I said sail of P is true. Okay, and so then I can say, oh, that person definitely loves the ocean. Okay, I am that person, so that's fine. This is actually a true fact. Did anybody know this? If you're not in Nova Scotia, it may not be as apparent, but everyone in Nova Scotia lives within 67 kilometers of the ocean. I looked up the number. Someone in Nova Scotia has never seen the ocean. Hopefully no one in my class. If not, as a person who loves to sail and loves the ocean, what conclusion can we draw and why? Someone in Nova Scotia lives within 67 kilometers of the ocean and has never seen the ocean. What is the rule that I'm applying here? Universal Modus Tollens, because essentially that first one says everyone in Nova Scotia lives within 67 kilometers of the ocean. Someone, now that's saying finding an instance where somebody has never seen the ocean, and so this is combining facts. Okay, so here's a question. I'm going to pick the all students in this class understand logic. Christian is in this class. Therefore, Christian understands logic. Is this valid logic? Agree, this is valid logic. Why can I say this is valid logic? What rule am I following? And how do I break it down? Yeah, so this one is Ponens, the universal Modus Ponens. How do I break it down? So if it's universal Modus Ponens, one thing that's not always obvious when we're working in the English language and we're trying to translate into this type of logic is I want it to be something of the form P of X implies Q of X, right? What's P of X in this case? I'll use C since Kristen starts with a C, and we're concluding Q of C. P of X is in this class. And so then Q of X then understands logic. And so the reason that this can be tricky when we talk about how do we break down language, and this comes down, this is also something that relates back to natural language processing, right? There are a lot of computer systems that are taking in information and trying to translate that into something that makes some sense. But to do that, right, computer systems work in this logic-based mode. How do you translate all students in this class understand logic to for all X, P of X implies Q of X? You have to understand which is P of X and which is Q of X, right? So this is the piece that takes a little bit of thinking. And it's a little broken down, a bit obvious here, because you could see then the next one I have, Christian is in this class. Christian understands logic. But if I didn't break it down as quickly, understanding that first sentence takes a little bit to consider. Okay, so is this valid logic? Adam, you have a short name, so I am going to use you. My pen is only working so well. I'm picking at random, but perfect. Okay, so every computer science student takes discrete mathematics. Adam is in this class, which is discrete mathematics. Therefore, Adam is a computer science student. So every computer science student takes discrete mathematics. Adam is taking discrete mathematics. Therefore, Adam is a computer science student. All right, so is this valid logic? Why is it, for those that said no, why do you think it's not? Implication can't go backward. So this looks a lot like one of the fallacies that we've looked at before, right? So in fact, we've got, essentially we say, so what we have is something like for all X, P of X implies Q of X. Every computer science student takes discrete mathematics. What does this one say? If you assume the class is discrete mathematics, what does that actually say? What it says is we have some element, Adam, in our thing such that Q of A holds. This is a problem because that doesn't tell us anything, right? He can be in this class and he can be a computer science student or not be a computer science student, but that implication doesn't tell us anything in that direction, right? It actually says another way of thinking about this, and you can use this just as we were able to say, so if you remember when we said P implies Q is logically equivalent to either Q being true or not P. We can do the same here, right? So that's like saying for all X, either Q of X is true or P of X is false, not P of X. Okay, so doesn't tell us anything other than the fact that Q of A is true. It doesn't imply anything else. And so we don't know. Like, luckily for us, we can just ask him because he's in our class. But it doesn't tell us anything from the logic.